Hey everybody, welcome back for episode 14. We're going to continue our work with integral applications and focus in on regions within the coordinate plane and different things that you might be asked to do with those. So I've given you a very basic graph here, and I'm going to define the first function here, f of x, and then my second function here, g of x, where they intersect at 0, 0, and then a and b. This is a very simple example to do this with. Be ready for this to be applied to applications or word problem or weird functions or other pictures, and I won't be able to hit everything here, but I should hit a pretty good amount within this review. So some things that you might have to be able to do with this region. First and foremost, you should be able to find the area. And remember, area is simply equal to the integral from 0 to a of the top function minus the bottom function. So f of x minus gx dx. Keep my proper notation, because it is a rectangle, right? Height of the rectangle is the difference in the functions. Dx is the width of each of those rectangles. The integral adds them together. This would give me the area. I could alternately do this in terms of y, if it was easier in that way for the problem, by doing right equation minus left equation, g of y minus f of y, dy. Okay, so that would, if you're asked for area enclosed, that's it. Very simple. Definitely could be something you have to do by hand as well. All right, let's look at some volume. So the first type of volume that we did was cross-sectional volume. And remember, for cross sections, the shapes change. And we learned a lot of very basic coefficients and shapes that you could use. They also throw in some different ones that might not be one of those basic shapes, and they might define the dimensions differently. But the whole idea is you're defining one of those partitions, whether it's a square or a rectangle or a triangle or semicircle, whatever it is, you're defining the volume of one of those little partitions. It's volume because it's three-dimensional, which I'll show in just a second. You can do these perpendicular to the x is in terms of x, because the cross section is defined this way, and its thickness of each cross section is a change in x, so dx. So when you set up your integral, excuse me, 0 to a, the area of the shape is generally some variation of top minus bottom squared, and then times the thickness of each partition dx. Now, what could change is a coefficient. You can review your notes, look at some of those different coefficients that we went through. If cross sections are perpendicular to the y, so if we head the other way, the setup is essentially the same. It's just right minus left, and 0 to b. So g of y minus f of y squared, and then dy. Again, the reason this time now the thickness of each partition is a dy, change in y, and then they pop up, and the area of that cross section is some variation usually of this, unless they define the dimensions some other way, where they say it extends horizontally from f to g, and vertically it comes up based on some other function. Then you'd have to do 2 dimensions times and then times the dy. So just focus on how it's defined. These are more for the basics, but be ready to apply the knowledge elsewhere. Okay, let's look at some other volumes, and I'm going to do the same region, and we're going to do our great rotation problem. So let me just get a quick sketch. A, B, F, and G. All right, some different rotations that you might get hit with. And I'm going to color code each of these. So rotate about, I'll call this number 3. Rotate. Let's start with the x-axis. If you are doing a rotation of volume, always be sure to have a picture and mark your axis of revolution. Then determine, is it a washer or a disk? Remember, a disk would be if this region was flush up against the axis of revolution, if there was no gap. Because this is a gap, it's a washer. So there are 2 radii. And I define each of those radii in terms of the function and from where I am drawing them from. So simply this time, it's just going to be f of x squared minus g of x squared dx. Big R squared minus little r squared. Okay, let's rotate around the y-axis. Now my radii come out this way, and they're perpendicular to the y. Each washer has a thickness of dy, a change in y. So I'm going to do it in terms of y. G of y squared minus f of y squared. And I always define the big radius first as the further distance out. That's why it's switched over to g this time. Now, what if the line moves? So let's say that you rotate about a line. I'm going to put it up here this time. Let's say that this is the line y equals 5. Let's say 5 is greater than b. Now, when I define my radii, they're perpendicular to the x-axis. It's a horizontal axis of revolution, so I'm still going to be in terms of x. So pi 0 to a. But now when I define this distance, it's not, the bigger arrow is not just g of x, it's the difference between 5 and g of x. So it's 5 minus g of x squared minus 5 minus f of x squared dx. Again, defining the larger arrow, that's my radius, my big R, and the smaller arrow, my little r. All right, one final rotation I want to hit with this graph is maybe it's something out here. Let's say we rotate around the line x equals -1. Now my 2 radii are heading this way, and they are perpendicular to the y. We're back into dy mode. So pi, and then 0 to b. And when I rotate this time, when I define these distances, right minus left, the difference between g and -1 is going to be g of y minus -1. So g of y plus 1, f of y plus 1. We add the distance of 1 to each of my radii. So g of y plus 1 squared minus f of y plus 1 squared dy. This should hit most of your different variations. Notice these are all washers, so look out for a disk problem where there's only 1 radius of rotation, when there's no gap to be subtracted out. All right, one final piece to finish this section out. Same graph, one more time. Or about the same graph, close enough, right? F and then G. So number 4, you might be asked to find the perimeter of a region. And perimeter is the chief application of arc length. Your arc length formula. I won't go into how this one works so much, but just reminds you of the arc length formula. Look out for regions that have straight sides. This one has just 2 curved sides, so it's going to be really easy. Sometimes there's a horizontal or vertical side you have to include when you do perimeter that don't require arc length. But what I will do for this one is determine the length of the arc for G and the length of the arc for F. So remember, arc length, I'll do it in terms of x, but it could be done either way in terms of x or y, depending on what was easier. And then it's the square root of 1 plus the derivative squared. This would give me the length along the path for f, and then I would add this to the integral from 0 to a of the square root of 1 plus g prime of x squared. So utilizing the arc length for both, adding those together to get perimeter. So again, be ready for this in other applications or with some other sides that are mixed in there, but know the arc length formula and be ready to use it if you see a problem. It's like this. Okay, guys, that's it for today. Thank you for watching, and I will see all of you next time.